Hi folks, welcome to GFG. In this video session, we are going to look into one of the important chapter of operating system, which is one of the module of operating system, and that is process scheduling, also known as CPU scheduling. Boys and girls, as far as GATE exam and other competitive exams are concerned, we have seen that a lot of times numericals and reasoning questions, theoretical questions were asked from this chapter, namely CPU scheduling or process scheduling. It is one of the important sub-module of process management. So essentially we are going to look into what is meant by CPU scheduling, what is the need for CPU scheduling, and what are the essential criteria which are called scheduling criteria for assessing the performance of scheduling techniques to find out which is the most efficient solution. And after that we will look into, as case studies, various CPU scheduling algorithms or CPU scheduling techniques. I may not be wrong if I say that at least so far in GATE papers for the past 20-25 years, I would say definitely 30 to 35 questions have been asked. 30 questions, of course, I can say, have been asked based on CPU scheduling. That is the level of importance of this. And boys and girls, this is one of the easy topic, also interesting also. I would suppose that the students would love to solve problems of CPU scheduling. So let's start without any much delay. So this is the Geeks for Geeks Telegram channel. You can join if you have not done. You can subscribe it. And this is my brief profile, as I've been telling. Just in case if you have not enrolled for my Telegram channel, you can do so for all the benefits. And as usual, the disclaimer, then this is a chapter, process scheduling or CPU scheduling. So boys and girls, before I start the basic concepts, I would like to emphasize what is the need for scheduling. Let's discuss this topic. What is the need for CPU scheduling? Unless and until you understand what is the need for scheduling, you cannot really make a full understanding of various scheduling techniques. So let's build up understanding with regard to this need for CPU scheduling. Why, after all, we need scheduling? So therefore, we'll try to understand that perhaps by means of a diagram. So imagine in a typical multi-programmed operating system environment, this is a ready queue, and let's say this is a processor, this is a CPU. As you know very well, one CPU, one processor can execute one process. So this is ready queue. Say for example, if I have multiple processes present in the ready queue, Pi, Pj, Pk, all are waiting to run on CPU. Okay, this RQ means ready queue, and these are the ready processes that are awaiting to get themselves to run on CPU. And because we said only one process can run on CPU at a time, so we need to decide essentially the process of making the decision is what is termed as scheduling. So we need to decide who should run next. So for that we use some selection criteria. So using that selection criteria, we implement the algorithm known as CPU scheduling algorithm to decide who should run next based on some criteria. So who is going to make that decision? So boys and girls, that decision is made by a component of operating system we have defined earlier called short-term scheduler. Is it not? We have seen that. So short-term scheduler is that module of operating system which is going to decide essentially which ready process should run next onto CPU. This is going to decide. So essentially this short-term scheduler is nothing but CPU scheduler. Is CPU scheduler. We told that point earlier at that time when we were discussing about schedulers and dispatcher. Okay, CPU scheduler or short-term scheduler is primarily responsible for deciding which ready process should run next onto CPU whenever the CPU is idle. So that is the need for CPU scheduling. So it can use several criteria, like natural criteria is arrival time. Whoever has come first should get scheduled first. Whoever has come last may get scheduled first. Whoever is having higher priority may schedule first. Whoever is having the least burst time may schedule first. Whoever is having lower process ID may schedule first. So I can have innumerable criteria, and perhaps in the exam they may devise a new criteria and ask you to solve a problem based on that. Quite possible. So, but however, as per the standard textbooks like Galvin, because we are discussing the content from Galvin textbook, so therefore we will study what are the standard scheduling criteria, scheduling selection criteria in order to implement the different scheduling algorithms. Okay, And this CPU scheduler can operate in two modes. Please remember that. There are two modes in which it can operate. There are two modes in which it can operate, as you studied earlier. One is called non-preemptive and the other is called preemptive. Any scheduling technique, any scheduling algorithm, so this is called mode of operation. It can operate either in non-preemptive mode or preemptive mode. Means, for example, non-preemption means once I schedule the process onto CPU, the running program will not leave the CPU, right, only under voluntary condition. It will leave the CPU only under voluntary condition. It will not leave the CPU forcibly. Nobody can force the running process to leave the CPU. It can release the CPU voluntarily. That is when it complete or need to go for IO operation. And the other approach is called preemptive, wherein the running program can relinquish the control of CPU forcibly by some parameter, using some parameter through operating system, like maybe time or maybe priority or maybe burst time or maybe several other such criteria. So any scheduling algorithm implemented by the short-term scheduler would operate in the mode of either preemptive or non-preemptive. So that's a classification of scheduling algorithms or scheduling criteria. So boys and girls, this is the approach. There is a need for scheduling. I hope by means of this diagram, it is definitely clear as to why do we require CPU scheduling or why do we need CPU scheduler, short-term scheduler. So essentially, this chapter deals with the design of short-term scheduler, is it not? This deals with essentially the design of short-term scheduler. So before we study the various scheduling criteria, the selection criteria, let's have some basic concepts, right? Basic concepts. Like first we say the basic objective of CPU scheduler is to maximize the CPU utilization through multi-programming. And then there is something called burst. So when you look at the word burst that you most often encounter in this chapter, the burst means basically duration of time. Burst means some duration of time. So there are two types of bursts that we use in process scheduling, CPU scheduling. One is called CPU burst and the other is called IO burst. The amount of time for which the process runs on CPU executing the instruction, that is called CPU burst. Like this is the class burst, the time which I am using to deliver the lecture, that is called burst time of my class, my lecture. Like that CPU burst, the time for which the process runs on CPU executing the instructions is called CPU burst. And likewise, when the process need to go for IO operation, the amount of time for which the process spend in performing IO operation, waiting for IO, performing IO operation, right? That whole time duration is called IO burst. So essentially, in the life cycle of the process, we have these two types of bursts, which is shown by means of a diagram given in the Galvin textbook. So here, boys and girls, if you observe, I have some instructions. So executing these instructions, whatever time is needed, is called CPU burst. And after this, the process has gone for IO because the instruction is read from file. So the moment it go for read from file, right? So the amount of time for which it waits for performing IO operation, completion of IO operation is called IO burst. Completing IO burst, again it can have CPU burst, again it can have IO burst. So that series will continue, that life cycle will continue. So essentially the process in its entire life cycle will have a series of IO burst and series of CPU burst. And boys and girls, in case if the process doesn't have any IO burst, such processes are called CPU bound processes. I repeat, the processes which does not have any IO operation, that needs only to run on CPU, that are bound to work only on CPU, execute only instructions on CPU, no IO operations. Such processes are called CPU bound processes, B-O-U-N-D, bound. Similarly, if the process spends most of the time on performing IO rather than computation, such processes are called IO bound. So it's a natural appeal that we should have a good mix of CPU and IO bound so that processor and the devices are kept busy. Otherwise, if I have only CPU bound processes present in my system, so CPU would be busy, IO devices would be idle. And if there are only IO bound processes, then input output devices most often would be busy and processor would be idle. So therefore, if we have a good mix of both CPU bound and IO bound processes, only then we can have good and effective utilization of the processor and the input output devices. So that's the point. So that is about the philosophy of CPU burst and IO burst. So CPU burst is followed by IO burst and so on, it continues. The CPU burst distribution is of main challenge or concern. If I have large number of short bursts and small number of long bursts, this is how basically the diagram would look like, the histogram would look like. The burst duration on the x-axis and the frequency of the burst on the y-axis. Short durations have a large number of short bursts and small number of long bursts. Okay. And here the CPU scheduler, as I said, it is of two types. So it can operate in non-preemptive mode and preemptive mode. That is being highlighted by means of these points. Please have a look at it. The CPU scheduler essentially selects from among the processes that are there in ready queue and allocate it, dispatch it onto the CPU core or the processor. And if there are multiple cores, it can assign it to one of the cores, one of the processor. The queue can be ordered in various ways. Like for example, I can implement the queue like a FIFO queue or a LIFO queue or a priority queue. That's what this point say, can be ordered in various ways. The decision can take place in any of these four conditions. Listen to this, this is a very important point. When do CPU scheduler get activated? When does the short-term scheduler get activated? When do I have to actually make a decision? There are four conditions. Look at this. When the process switches from running to waiting state, running process need to go for IO, CPU become idle, I have to decide who should run next. Switches from running to ready, when the running process gets preempted forcibly through some interrupt or through some priority, leaving the CPU idle, we have to decide who should run next. Switches from waiting to ready. Like process completed IO, it goes to ready queue, perhaps it may interrupt the running process, it may have to run on CPU, we have to make a decision. And finally, when the running program completes its execution, terminates, we have to make a decision. For situations 1 and 4, boys and girls, for situation 1 and 4, it is called, there is no choice for scheduling. A new process, if any exists, must be selected for execution. But for situations 2 and 3, we have a choice. So for 1 and 4, the going from running state to waiting state and terminate, these are voluntary conditions. And that's why the type of scheduling for 1 and 4 is called non-preemptive, and for 2 and 3 it is called preemptive. Scheduling done in case of 1 and 4 is called non-preemptive. We don't have a choice, we have to schedule. But for 2 and 3 we have a choice. So therefore it is preemptive approach. That's what comes here. When scheduling takes place under conditions, circumstances 1 and 4, the scheduling scheme is known as non-preemptive. Check it. In case of 1 and 4, it is called non-preemptive. I told, otherwise it is preemptive. So boys and girls, this is a very important point. So do also remember that under non-preemptive mode, once the processor has been allocated to a process, the process keeps the CPU until it releases it either by terminating or switching to waiting state. This is non-preemptive. And virtually all modern operating systems, including Windows, Mac OS, Linux and Unix, use preemptive scheduling algorithms. This is an important point to keep in mind, and I would not be wrong if I say this is essentially an interview tip. Then interview tip. I'm marking with a star to indicate that this is an interview tip, a flag. Okay, it's an interview point. Like for example, in this regard, I would like to also pin a point here. What is that? The point is, see, the discussions with regard to the implementation that we are going to make here, like the implementations of different scheduling algorithm like first come first serve, round robin, priority, etc. These are generic scheduling techniques, generic. They are not in reference to any particular operating system. But your responsibility when you are preparing for placements would be, after making a study of this, after learning from my videos all these scheduling techniques, essentially it is your responsibility to find out, particularly in Windows latest version like Windows 10, Windows 11 for example, or Unix or Linux or Mac operating system, which scheduling technique is done, or how essentially CPU scheduling is carried out in these contemporary modern operating systems. That is your responsibility, boys and girls, because that becomes slightly out of scope of my lecture. Okay, so because we are discussing the platform in a generic way, so after that you can just refer, maybe you can use ChatGPT, or maybe you can use Google, or maybe you can use the websites of these companies like Microsoft, etc., to find out essentially how scheduling is done, which scheduling technique is used, what scheduling criteria is used, selection criteria is used, which scheduling algorithm is used in these contemporary operating systems, and that also may be a good interview tip. Okay, So let's continue. And we have already seen, boys and girls, in my earlier session, dispatcher works in unison with scheduler. Or I may not be wrong if I say dispatcher is a worker of short-term scheduler. Short-term scheduler is a manager and dispatcher is its worker. What is the role of dispatcher? In the earlier session, if you remember, we said dispatcher carries out the activity of context switching. Context switching is an activity carried out during a process switch. When I am switching from one process to another process, when due to the process completion or IO or any other timer interrupt, preemption, running process leave the CPU, I may have to save the PCB. And then I have to load the PCB of the next process who is going to run. So who is going to do that activity? Saving and loading the PCB, we said, is carried out by dispatcher. But do remember a very significant and important point. Dispatcher does not make any decision. Sometime in the interview, people may ask, bro, what is the difference between scheduler and dispatcher? People may ask. Scheduler decides, dispatcher implements the decision, carries out the decision. So that's what we said. Dispatcher is a worker of scheduler. Scheduler responsibility is to make a decision who should run next. Then it will pass on that decision to dispatcher to execute it, to carry out. It is like in any institution, college, we have board of governors. Board of governors will make policies, will make the decisions. And then the principal, the HODs and other faculty will have to carry out their decisions. That's it. That's the point. Okay. So dispatcher module gives control of the CPU to the process selected by the CPU scheduler. That's what I said. So it's very clearly given in the textbook of 𝐂𝐤𝐚𝐿. Look at that. Gives control of the CPU, dispatches the process onto the CPU, who is selected by the CPU scheduler, short-term scheduler. This involves switching the context, switching to user mode, jumping to the proper location in the user program to restart that program. And the amount of time invested in loading and saving the PCBs is called context switch time, also called dispatch latency. This is already done, and diagrammatically it is shown here. Some process PI is executing, it got preempted. We have saved the PCB of PI, restored the PCB of another process PJ, and PJ starts executing. This whole duration of time spent by dispatcher is called dispatch latency or context switching time. Okay, so that's the point. Then, boys and girls, as I said, whenever we have any problem, the problem may have multiple solutions, is it not? A problem may have multiple solutions. Like, I may have multiple algorithms for solving a problem. Sorting. There are many sorting techniques: selection sort, bubble sort, insertion sort, heap sort, quick sort. Then obviously when I have multiple solutions, multiple algorithms for solving a problem, anybody would be interested to know, sir, which is the best, which is efficient. So likewise, there are multiple scheduling techniques. Then people may ask, which is efficient, which is best. So to assess who is best, which is best, we need some criteria. Performance criteria. When I want to compare two students, I should compare with respect to some criteria like marks, rank, right? Some criteria like that. So like that, when I have multiple scheduling techniques, I should have some criteria to compare them in order to find out. That is called performance comparison, in order to find out which algorithm is superior, efficient, or in general terminology we say best. So what are those criteria? The criteria is CPU utilization. A good scheduler is one, an optimal scheduler is one that keeps the processor busy most of the time. Is it not? That's very obvious, very common sense. And maximizing CPU utilization. Maximizing CPU utilization would result invariably in what? Invariably in increasing the throughput. Sir, what is throughput? Please remember, throughput is number of processes completed per unit time. Throughput is a metric which is associated with any running system. Boys and girls, the lecture that is going on, if you consider that as a system, my lecture also has a throughput. Sir, what is throughput of the class, of the lecture? Throughput is the number of units or maybe the number of topics that I covered in the duration of the lecture. So for example, if the duration of the lecture is 60 minutes, in 60 minutes if I complete 10 topics, so in 1 second, 1 minute, how many topics have been completed? 60 minutes, 10 topics, 1 minute, how many topics? So therefore 10 by 60, that is throughput, 60%. If I waste my time, throughput decrease. So obviously, one of the objective of the design of short-term scheduler should be to maximize the throughput. The objective of the lecture should be to maximize the throughput, but that doesn't mean at the state of compromising on the quality or the efficiency. Okay. At the same time, we have to see that all topics are covered and effectively covered and all the essential things are covered, etc. So throughput is that. There is another parameter called turnaround time. We are going to describe this, what is turnaround time. We are going to cover a small topic under the banner called process times, where I will explain turnaround time. These are metric basically. We write in short TAT. The turnaround time, in a very simple or generic way, I can say that it is the total lifetime spent by the process in memory from its arrival till its completion. That is called turnaround time. Okay. The whole duration of the lecture which I spend, which includes some breaks perhaps. Suppose I am taking a very long lecture for 6 hours or maybe more than that. I mean, indefinitely I have scheduled the class. I would say that today the class will start at 9 a.m. I don't know what time it is going to complete. So the whole duration of time that I spend from 9 a.m. till I complete the lecture, which includes several breaks, lunch break, tea break, etc., that is whole called turnaround time. I hope the concept is clear, but of course, when I make a diagram, or I'll explain it by means of a simple diagram, kindly see. Like that, there is another parameter, another metric called waiting time. We write waiting time generally in short as WT. Sir, what is waiting time? The amount of time spent by the process waiting in the ready queue, right? Not running on CPU. It got entered into ready queue, but it is invariably waiting to run on CPU. So the amount of time for which the process wait in the ready queue is called waiting. Class was announced at 9 a.m. for example, and the lecturer or the teacher, the educator has not turned up. So students are keeping on waiting in your system. That is called waiting time. Waiting to start the lecture. You are ready and waiting to start or listen to the lecture. Okay. So naturally you want to minimize the waiting. There is another parameter called response time. Amount of time it takes from when a request was submitted until the first response is produced. Response or result to the time admission of the request, the duration of time is called response time. I generally used to give this example for instance, because there are two types of response time. One is response time of the process and the other is response time of the request of the process. Response time of the process is time of arrival to the time at which it gets onto the CPU for the first time. That is called response time of the process. Sir, what is response time of request of the process? Boys and girls, every process may be associated with several requests. Sir, what is this request? Simple example, you open a browser. In the browser, I can have several requests, for example, pending on the web page. Okay. There are several hyperlinks. If you consider, you imagine, for example, every hyperlink is like a request. So the moment you click one hyperlink, for example, click one hyperlink, the time you click and the time taken to deliver the response of that hyperlink, maybe in the pop-up window or maybe in another new window or another tab, that is called response time. If you want more example, maybe in the class, for example, physical mode classroom, physical classroom. The teacher like me asks a question to the class, say that whoever gives the answer will be rewarded. Then the students start working. So the moment I complete my question to the moment some student give the response, give the answer, that is called response time. Hope you understood the meaning of response time. So boys and girls, these are the important metrics, criteria which are generally associated with process to assess, to find out, to make performance comparison among different processes to find out which scheduling technique is superior, better, efficient, optimal. Okay, these are scheduling criteria. The metrics, the parameters which are used to make performance comparison among different scheduling techniques in order to find out the efficient CPU scheduling algorithm. So what you would like to do, what is the goal of this CPU scheduler? The goal is to maximize the CPU utilization, minimize the turnaround time, minimize the waiting time, minimize the response time. So let me underline response time also. That is also an important parameter. Is it not? Sorry, already done. So throughput has to be underlined. These are 1, 2, 3, 4 metrics which you would like to see here I have given. As an operating system developer, as an operating system designer and developer, what is your objective with regard to these criteria? Your objective would be to maximize the CPU utilization so that the throughput gets maximized. These are interrelated. If you maximize the CPU utilization, obviously the throughput will increase. Minimize the turnaround time, minimize the waiting time, minimize the response time. These are called scheduling criteria. objectives of criteria. A good scheduler is one which will maximize the throughput, minimize the turnaround time, minimize the waiting time, minimize the response time. Got it? And to improve the focus further, I will make more clarity and I will give you some formulas for computing the turnaround time, waiting time and so on. How do you compute? So see on board. So I will name this topic, small topic, as check. From my side, I will say process times. That means what are the different times a process is associated with? What are the different times a process is associated with during its lifetime? During its lifetime. What are the different times a process is associated with during its lifetime? So let's start. We'll understand this diagrammatically. Okay. Let's say this is the life cycle of the process. Okay. Let's say this is the life cycle of the process. The very first time with the process is associated with is called arrival time. Some people call admission time, submission time. Invariably, I will call arrival time, written in short, AT. The time at which the process enters into the ready queue for the first time, the time at which the process gets itself admitted into the ready queue, this is ready queue. First entry into the system, first time it enters the memory, that is called arrival. New to ready, transition is new to ready, that is arrival time. And the time for which the process spent in the ready queue, waiting to run on CPU, is it not? It is waiting to run on CPU. So this time is called waiting time, WT1, because I can have multiple waiting times. So therefore, next time is called waiting time, WT, waiting in ready queue. Waiting for what? Waiting to run on CPU. Like for example, it got scheduled onto CPU. This time is called scheduling time. I can have multiple scheduling, so I'll put ST1. And the duration of time for which the process runs on CPU executing the instructions is called burst time. I can have multiple burst time, so therefore I'm writing BT1. So this is CPU burst or simply burst time. So boys and girls, please remember this is actually CPU burst, but we write in short for simplicity burst time, BT. After running on CPU for some time, perhaps the process may need to go for IO operation, IO device. So this amount of time for which it spent performing IO operation, the amount of time for which the process spent performing IO operation is what is termed as IOBT. I can have multiple IO burst time, but however, let us write it like one here. Input, output, burst time, IOBT. Okay, CPU burst, BT, IO burst, IOBT. Then after completing of IO burst time here it got completed. Where will the process come back? Is it not? From block state to ready state. So it will come back to ready queue again. It will come back to ready queue again. And it waits in the ready queue again to get a chance to run on CPU. This is another waiting, WT2. And again it get a chance to run on CPU. Is it not? This is another scheduling time. This is another scheduling time, ST2. And for the time for which it runs on CPU is another burst, BT2. And perhaps imagine, for example, it got preempted here, PR, preempted. The process got preempted because of several reasons like time quantum expiration or whatever. Is it not? So it get preempted. Where will the process come back to? The process will come back to ready queue. Is it not? On preemption, the process will come back to ready queue. For what? Waiting to run on CPU again. So there is another waiting, WT3. And again another scheduling here, ST3. And it get a chance to run on CPU again for another burst, BT3. And this life cycle continue. And finally, this is your completion time, CT, last time. The time at which the process completes its execution is called completion time. So boys and girls, this is a very important topic illustrating what are the different times a process is associated with during its life cycle. This may also include suspend time in case if the process is getting suspended, but just for simplicity, I am not showing it. Otherwise, in case if the process gets suspended, then that also will be included in this. So boys and girls, in respect of this diagram, I would like to make a mention that the duration of time spent by the process starting from its arrival to completion, this whole duration of time is what is termed as turnaround time. This whole duration of time is known as turnaround time. All right, turnaround time. So based on this, I am very sure you can propose a formula for turnaround time. What will be the formula? Very important concept. The formula for turnaround time, we write in short TAT, will be nothing but completion time minus arrival time. This is a formula to be noted, because many a times in solving problems we are going to use this. Is it not? Turnaround time is equal to completion time minus arrival time, the whole duration. And from here, if you want, because metric is waiting time, so therefore what will be the formula for waiting time? Remember, waiting time is the total time spent by the process in ready queue, not the IO queue, only ready queue. Waiting time in ready queue. As per the formula, if you observe, if you want to calculate the total durations, of this waiting time, WT1 plus WT2 plus WT3, this total duration, because process may have many waitings. So in general, what will be the formula for waiting time? The formula for waiting time will be, from total to turnaround time, you have to subtract total burst time plus total IO burst time. Subtracting these two will give you waiting time. And as a consequence to this, I can say that waiting time is equal to turnaround time minus burst time, provided, just in case, if IO burst time is equal to 0. In case if the process doesn't have IO burst time, look at that. In case if the process doesn't have IO burst time, if IO burst time is 0, then the formula, what will it become? Turnaround time minus burst time. So boys and girls, these are very, very important formulas as far as CPU scheduling is concerned, or problem solving with CPU scheduling is concerned. Turnaround time, waiting time, because those were the metrics here. Turnaround time and waiting time. How to calculate throughput and how to calculate response time, I will show you after some time. Hope this concept is clear. As a consequence to this, I would also like to make a mention here for your convenience. Imagine, for example, if there are n processes, boys and girls, please follow. If there are n processes sequentially numbered P1 to Pn. Okay, let's say the arrival time of the process Pi, particular process, is given as Ai. The total burst time of the process Pi, let's say, is some Xi. And if you have also IO burst time of process Pi, let us denote it as Yi. And if the completion time of process Pi is given as Ci, if this is my framework, then I would like to make a mention that, I would like to tell you that, see on board, for a given set of 3 processes, suppose if I take, got stuck, just, so if I take a particular value of n, like for example, if I take 3 processes, if I take 4 processes, 5 processes, n equal to 3, 4, 5, then I can schedule them in different orders. Maybe first P1, then P2, then P3, or maybe P2 or P3, then P1, 3 processes, or P1, P3, P2, something like that. So I have n factorial orderings. Those are called scheduling orders, scheduling sequences, number of schedules. So those are non-preemptive schedules. So for non-preemptive schedule, for a set of n processes, I can have n factorial scheduling. So let us write that point. Okay, let us write that point. For a set of n processes, I can have n factorial scheduling, and the total amount of time needed to schedule all n processes as per a schedule, total time taken to complete all n processes as per a schedule, is known as schedule length, or length of the schedule. Schedule length or length of the schedule. So how to calculate that? Maybe perhaps, I think the system slightly got stuck. I think there is some problem with the smart board. It's got stuck. So I think I will close this session here, and in the next session I will continue from here in part 2. So part 1 of scheduling we have seen all the scheduling criteria. So in part 2 I will take up the discussion completing this number of schedules and schedule length, and then we'll start with the first scheduling algorithm or the list of scheduling algorithms, starting with like first come first serve, and then priority, round robin, shortest job first. Everything will cover one by one sequentially. So next video we'll start the discussion with different scheduling algorithms and in fact with different problem solving. Okay, thank you.